Okay, so our project was called Offline RL for Real-Life Data with Events from Challenger LoL matches. LoL standing for League of Legends. And it was been made in a team of me, Adrian Górecki, with Michał Szumielewicz and Krzysztof Rymski. And it has been supervised by Dr. Jacek Saranka. Okay, so first I will start by talking a bit about League of Legends, the game that we train our data on and worked on. It's an online game with matches that always contain 10 players. The players are separated into two teams, so we have 5 versus 5. Before the game starts, all players always choose one champion that they will play as, and few other things like called, for example, runes that enhance their champions a little bit, like give them additional abilities. This will matter a bit later. During the game, the champions gain gold and experience for the things they do, and with that they get stronger, they have more power, and so the team that manages to fulfill some objective will get stronger and more likely to win in the future. And in the end, the goal is to destroy all the structure, enough structures of the enemy base, and to finish the game. What matters for us is that how the data is structured. That we have from 15 to 40 minutes of data that is sequential, that the events that change the course of the game, and then events at the beginning of the game will matter for the rest of it. And what we wanted to do with the data is we wanted to mainly predict which team will win. Why the game was chosen in the first place was because the API of this game is publicly available. So all the information about the matches is publicly available. The game is very popular. So there was a huge amount of data that we could train on and we could use for our experiments. During those, we also wanted to be able to check which features are the most important for the game result. And we wanted to benchmark machine learning models with other approaches that are, let's say, more basic. Okay, so let's first start with our data, what we worked on. As mentioned before, we sourced everything from the publicly available API. In the end, we worked on around 115,000, like just a bit over, matches on Challenger level. Challenger is what the game calls the best players on the given server. So what we worked with was pretty much only the data of the best. So there was very little. There was no really like a lot of improper plays. We could assume that the players were playing quite correctly. In each of the matches, we had around 2,000 per match, though it varied quite differently from match to match. Snapshots, and each snapshot contained information about what happened in a given moment of the game, and statistics of all champions and everything that was in the game at the time. So, for example, if someone gained a new level, it was noticed. If one of the players died, it was in the dataset, and all events like that were there. Also, I think there was one snapshot every minute, additional one. But those were only small percentage of them. But yeah, we also had like periodic snapshot each minute. Yeah.
I think it's like the snapshot per minute was for the meta statistics and.
Oh, okay. So yeah, that doesn't matter. But yeah, but what important is that the information we had was not some continuous like data from each second of the game. We only could look at specific snapshots. We had quite a lot of those, like 2,000 per match, where matches are around 25 to 30 minutes, like on average, is quite a lot, but still we didn't have all the data about the match. So this is what we had to work with. We wanted to compare our solution with three baselines. We wanted to check, like had a basic check, if with gold difference. So we just counted the amount of gold because that's the most important. That's the thing that gives the most power to players. We checked the sum of gold in one team, in another team, and we said that the team with more gold will win. The second baseline model we tested was linear regression. It was just a simple linear regression trained on our data. And we had also XGBoost, which is a boosted tree model, which in general is quite good at this type of tasks, like categorical tasks. So that's what we included. And those were its performances. Here, maybe I will explain what the graph is, like what it exactly contains. For each match, this is accuracy in percentage of a given match. So for example, at 50, we'll see how accurate those models were in exactly the half point of each match. There we could have done we could tested a few different graphs, for example, like per seconds of the match, but because the matches were differing in length by quite a lot, like we had both 15 minutes matches and 50 minutes matches, we found out that this kind of graphs were the most representative of performance of models, so that's what we use the most of the time. And yeah, we can see that the most important thing is that we can see that gold advantage is quite good at predicting the winning team. Like, let's say at half a point of the games, it had more than 70% accuracy. And our linear regression was very similar to it, so we assume that it mostly probably just checked the goal difference, and it was mostly based on that. XGBoost was better than more of them, especially we can notice that at the start of the game, it had above 60% accuracy, which is quite impressive because at the start of the game, it was only the selection of things that the players do before the game starts. So like the aforementioned champions and runes. So just based on that, it had already 60% accuracy, which also tells us that they were important a lot. And so yeah, we also tested our data set, like around those kinds of things. So like what kinds of things matter a lot. This is, for example, how the probability of a team winning if they take an objective called a dragon. So if they slay the dragon, what is their chance of winning based on the dragon type? We can see that slaying any of them as the first team jumps our win percentage to almost 70%, with one of them being more important. Also, there are like other statistics that we can check. One of them gives us almost 80%. It also differs a bit which team it is because the map is not symmetrical. So we can also see that this was also part of our data. Okay, this is other statistic, but I think we can skip them. So we then tested our feature importance on our XGBoost model. So what things XGBoost took into account when determining the winning team. And we can see that it was mostly the champions they selected or perks, so like its internal name for runes. It based its selection mostly on the things from the start of the game. And as we could already see, the objectives that the players can take, even just like one at the start of the match, because like they often are taken at the start of the match, can change our win percentage a lot. And XGBoost didn't really look at them because of the nature of the model. It only took at singular snapshots. It couldn't check a lot of it. I mentioned, so we decided to train a transformer model on this data. But first we had to do a lot of data processing. I think we had to do for transformer model, though we did, in the end we used the processed data for all of the baseline models. It was, but that's not really that important. I will not say a lot about this, but because it's not very interesting, we had to, but because how Rails API provided the data, we had to change it quite a lot. We had to combine a few different files, we had to filter quite a lot of things, we had to reindex, we had to encode some of the stuff. We also added some expert variables on our own. So we spent quite a lot of effort on actually having the data set, which was necessary for everything. But I don't think there is, we will not talk about it too much here because the specifics are not really interesting. It was just kind of busy work or chores that we had to do. Okay, so to our transformer that we chose. We chose it because like our data is sequential, and it kind of makes sense that to use a transformer model for all of this. We took each snapshot as one token. So if we, like, for example, see how transformers are used in natural language processing, each snapshot we could kind of interpret as one word in natural language processing. It was like equivalent. So each game was one sequence, like in. So that was our approach. We only tried encoder. Because we didn't try to predict next snapshots. We only wanted to have an internal value for the performance or the win chance. Also, before we actually our data reached the transformer layers, we did some embeddings. We had some linear layers to also simplify the data and make it change it into tokens that could be processed by the transformer. And in the end, our tokens had dimensionality around 700. It was just above. In the end, it was, I think, 760 in our final model. So we spent quite a lot of time trying to engineer the best way to do this. And how did it perform? That's the graph of its performance. It doesn't look so bad at first, but then when we look at the comparison to other baseline models, it's not the best. It barely beats Gold Advantage. And we tried to find out why. And we found out a few things. The biggest problem was data normalization. With the data we had, normalizing it and making it not explode our gradients and completely destroy the training process. We had to put in the end normalization in a lot of places where it's because of our data was quite different than other users of transformers in other domains. The correct approaches for data normalization didn't work for our cases. If you use, for example, the same normalization that are usually used in transformers, our gradient still exploded, so we had to use a stronger normalization, which in our experiment seemed to decrease our both training speed and accuracy, but it was like the case of we had to sacrifice our accuracy for numerical stability. So we assume that's like our biggest problem. And if we were to like take next steps, if we were to improve, had the time to improve the model more, or if someone else would to try to improve this, the data normalization would be probably the biggest thing to look on. Also, our structure and hyperparameters, while we selected them quite carefully and tested them a little bit, we didn't have the time to retrain the model on each possible values, so they could probably be more changed. For example, specifics like the end of our encoder that was a linear layer, like the structure of this, or like our embeddings could probably maybe be more improve more. And also our dataset, as mentioned before, only included the best players. Maybe in making it a bigger one, having players from lower skill levels or just more matches could also improve performance. Yeah, those are our like probable causes why the performance was a bit disappointing. And our main conclusion from this was that you cannot just take taking a transformer model into a completely different domain, even when usage of transformer makes sense, is still quite a lot of work, and the details have to be improved a lot. So in our final report, we'll include the source. So if anybody would want to look at how we approach the transformer model and how we try to do this, we welcome everyone, and maybe they can find some room for improvement as well. But yeah, those are our findings. So I will go back still a bit for the performance of the transformer. This is what we managed, and maybe someone else will try to manage to improve our work and use the transformer models or other machine learning models in this scenario. And yeah, that was all. Thank you.